humans are fascinated by exploring the unexplored. A vast majority of our water bodies remain unexplored primarily because of the difficulty in accessibility. A person equipped with the right breathing apparatus can dive to the seafloor for exploring. It's also an adventure sport. Sometimes, however, at certain depths below the sea level, divers experience a loss of consciousness. It leads to all symptoms of intoxication, such as short term memory loss, numbness, hallucinations, and so on. This effect is reversible, meaning that upon rising back to the surface, they regain back consciousness. However, in certain cases, it may prove fatal. This loss of consciousness is called as nitrogen narcosis. Hello, my name is Aditya, and in this video, we're going to look at what does fluid mechanics have to do with nitrogen narcosis. Let us first consider the pressure at a point. The important characteristics of pressure are that it is normal to the surface area, and that it acts in a way that it is compressive. So if we have a balloon like this, the external pressure will always act normal to all the given points on the surface of the balloon, and it will always act in such a way that it tries to compress the balloon, unless of course the pressure inside the balloon is larger. Now, in order to assess the fluid pressure at a given point, let us consider a wedge like this with lengths delta y, delta x and delta s. The pressures are acting normal like this. Let us call this px, let us call this py, and let us call this as p. Because we are considering a 2D problem, let us consider that the width into the plane is equal to b. Let this angle be theta, and if that is true, then this angle the pressure makes with the vertical is also theta. Let us write down the force balance in the x direction. So it will involve px times the area on which px acts, so basically delta y times b, minus the force due to the pressure acting on the slant face, which is p delta s times b, and the component in the x direction, which will be sin theta. This will be equal to 0. Similarly, in the y direction, we have py times delta x times b minus p times delta s b, and the component in the y direction of this force, which will be cos theta. Apart from these two surface forces, we will also have the weight of the fluid element. So if the density is rho, then the volume, which is delta x delta y by 2 multiplied by b, so this is the total mass of the fluid element, and times gravity, this will be total weight. So rho times the volume times g, and this will be equal to 0. From elementary trigonometry, we have delta s cos theta is equal to delta x, and delta s sin theta is equal to delta y. So let us simplify the force balances. We can cancel out b from all these terms, and the fact that delta y and delta s sin theta are equal, we can cancel out this. So the x force balance gives us px minus p equal to 0. Now let us divide everything by delta x. So this delta x cancels out, and we divide everything by delta x. So this delta x cancels. Now delta s cos theta is equal to delta x from trigonometry. So even this particular term cancels out, and we are left with py minus p minus rho upon 2 delta y times g is equal to 0. Now in order to find out the force at a given point, we must shrink this particular fluid wedge to a given point. And how do we do that? We let delta x and delta y go to 0. But do they go to 0 arbitrarily? The answer is no. They must go to 0 in such a way that it preserves the similarity of this particular triangle, that the angle between the slant and the horizontal will always be theta. So we shrink it in that manner. So delta y and delta x simultaneously go to 0. The only term which contains delta x or delta y is this particular term, and if the delta y goes to 0, this particular term goes to 0, and we are left with py minus p equals to 0. So if we combine the results from the x force balance and the y force balance, we have p equal to px equal to py, which means at a given point it doesn't matter how you look at it, it is equal from all sides. This means that pressure is not only normal to an area or not just compressive, but it is also isotropic. Let us now find out the force on a fluid element because of pressure. So for that, let us consider a cube like this. So if we consider that on this particular face, the pressure acting is P at x, y, z, right? And I mean, if given that we are considering statics, it doesn't really matter if we write time over here. And if this length is delta x, the pressure on this particular face will be P x plus delta x, comma y, comma z. Now let us write down the force balance in the x direction. So it will be P at x, y, z times the area. So if this is delta x, this is delta y, and this is delta z. So P at x, y, z multiplied by delta y times delta z minus P at x plus delta x, y, z times the same area is going to be the differential force in the x direction. So dfx is pxyz minus px plus delta x, y, z, this whole term multiplied by delta y, delta z. Let us make use of Taylor's theorem or Taylor series expansion to write down P at x plus delta x, y, z as P at x, y, z plus del P del x at x, y, z times delta x plus 1 upon 2 factorial del 2p del x2 at x, y, z times delta x square and so on. And if we rearrange this, we have P at x plus delta x, y, z minus P at x, y, z is equal to del P del x delta x plus half del 2p del x2 delta x square, where it's understood that the partial derivatives of p with respect to x and the higher order derivatives are evaluated at x, y and z, basically at this point. So if you substitute this over here, we have this whole thing will be equal to minus del P del x delta x minus del 2p del x2 delta x square by 2 and so on times delta y delta z. So this is basically equal to minus del P del X, delta X, delta Y, delta Z, minus 1 by 2 del 2P del X2, delta X, delta Y, delta Z times another delta X, because we have delta X square over here. Now dfx upon delta X, delta Y, delta Z, essentially, which is equal to the force per unit volume, is equal to minus del P del X minus half del 2P del X2, and these particular terms cancel out. So you have delta X. So the force per unit volume in the X direction is equal to minus delta P del X plus delta X multiplied by all other terms. And if we let the volume of this cube shrink to 0, that is, it shrinks to a certain point, an infinitesimally small cubic element, and all these higher order terms will be 0. So these higher order terms will correspond to all the other terms in the Taylor series expansion. As a result of this, dfx will be equal to minus del P del X. Extending this, one can easily show that dfy will be equal to minus del P del Y, and dfz will be equal to minus del P del Z. Combining these three results, we can write df vector as dfx vector, or rather not dfx vector, dfx in the I direction plus dfx in the j direction, dfy in the j direction, and dfz in the k direction. And this is equal to minus del P del X I minus del P del Y j minus del P del Z k, and this essentially is minus gradient of P. So D small f is minus gradient of P. So the force acting on a fluid element is only if there is a pressure gradient. Now what exactly do we understand by this pressure gradient? So let us consider equal pressures at equal x values. So suppose this is x equal to 0, suppose this is x equal to 1, suppose this is x equal to 3, and say the pressure values are 100 Pascal, 50 Pascal and 10 Pascal. So because it's a one-dimensional variation of pressure, we can write the df as only dfx, and that will be equal to minus dp dx. Let us consider the first cell. Inside the first cell, let us find out what is dp dx. So it will be p at 1 minus p at 0 divided by 1 minus 0, which will be equal to 50 minus 100 divided by 1 is minus 50. So minus dp dx is equal to 50, meaning that the force acting on the fluid in the first cell is equal to 50 acting in the positive direction, because minus dp dx is the direction of the force. It is not dp dx, it is minus dp dx, minus of the gradient. What about cell 2? In cell 2 we have dp dx as p at 3 minus p at 1 upon 3 minus 1. Essentially it is 10 minus 50 upon 2, so minus 20. But minus dp dx in cell 2 will be equal to 20, meaning in this particular cell the force acting on a fluid element is 20 acting in the positive direction. So minus dp dx is sort of the direction from a higher pressure to a lower pressure. So if we have contours of pressure like this, so contours of pressure like this, where this is 100, 90, 80, 70, 60. So this is like a typical isocontour map. Okay, so then the gradient of P, or rather the negative of the gradient of P, will be lines which will be orthogonal to all the isocontour lines. It will be orthogonal to all the isocontour lines, and it will point in a direction going from higher pressure to lower pressure. So the direction is shown like this, and these are the directions of the force acting on the fluid element. Okay, so negative pressure gradient drives flow, and in this case it creates force. The pressure may be quantified in terms of either absolute pressure, that is the pressure with a zero reference point, or relative pressure. So typically we measure pressure relative to the atmosphere. So consider the surface of a lake. So if you go to a certain depth, the pressure increases. So if I call the pressure at the surface as P1 and the pressure at depth as P2, then P2 minus P1 is the gauge pressure at point 2. So gauge pressure is the pressure at a point relative to the atmospheric pressure. Similarly, we have vacuum pressure. So consider this as sea level, and as we go further up in the atmosphere, the pressure reduces. So if I call this point as 2 and if I call this as P1, then P1 minus P2 is called as P2, vacuum pressure at point 2. It is the pressure relative to the atmosphere, how low the pressure is relative to the atmosphere. There are various instruments to measure at absolute pressure. They are called as absolute pressure gauges, but typically we have pressure gauges which give us readings with respect to the atmospheric pressure. There are also some kinds of pressure measuring devices called as differential pressure probes. So if we have two probes of a differential pressure probe, we will always obtain delta P between the 2 points, and typically the delta P is transduced into a current which we can further transduce to voltage or directly read out the current as a certain pressure difference. Let us now consider the fluid element, but now we account for its weight as well. So the forces acting on the fluid element in the z direction will be the one that will be altered. So we have already found out that because of the surface forces, the force acting in the z direction will be minus del P del Z. Apart from this, the force because of the weight will be minus rho times G. And we have removed volume from this particular term because this particular term was done per unit volume, and similarly this particular term is also per unit volume. And if the fluid element is in equilibrium, then this will be equal to 0. At the same time, we also note that del P del X will be equal to 0 and del P del Y will be equal to 0 because the fluid element is in equilibrium. But we are more concerned about this equation. So then we have del P del Z is equal to minus rho G. But if del P del X and del P del Y are equal to 0, then P is at best a function of Z. This will automatically satisfy these two conditions. Thus we can write dP dz is equal to minus rho G. So we can integrate from point 1 and 2. dP dz is equal to minus integration of rho G dz from 1 to 2. The left hand side is simply P2 minus P1, and this will be equal to minus integration of rho g going from 1 to 2 dz. Now if rho times g is constant, then what do we have? P2 minus P1 is equal to minus rho g z2 minus z1. And this is a very useful equation from the point of view of manometry. I mean, we'll solve problems in a separate video, but this is how we can find out. So if we have a surface of the lake, and if I call this point as 1, then how do I know the pressure at point 2? Well, to this particular equation, I know that P2 minus P1 is equal to minus rho g z2 minus z1. And if I set z1 equal to 0 and P1 equal to the atmospheric pressure P0, I have P2 minus P atmospheric is equal to minus rho g z, where we recall that z points upwards. But I can very well make a coordinate system where the depth is h equal to minus z2. That is, I want to represent the depth by a positive number, then I can very well write it as rho g h. So P2 gauge will be equal to rho g h. So as the depth increases, the pressure also increases. The Dead Sea is considered to have one of the most saline water on the planet, and that allows one to float freely on that. It almost feels like being weightless. However, the density of even that water is not that much different from that of fresh water. Of course, that small change in density gives rise to the buoyancy our body experiences. More on buoyancy later. However, the change in density is less than 5% even if we consider the salinity of the deepest ocean. I leave this as an example for you to Google out and find. This allows us to neglect the variation of density in liquids. Now naturally we come to the question whether G can be considered to be constant. Now we all know that G depends on 1 upon r square, where r is to be measured from the center of the earth. As a result of which we can write G equals G0 times r0 square upon r square, where r0 is approximately 6,400 kilometers. And if we consider r at an altitude of 10 kilometer or even 20 kilometers, which is the altitude of supersonic flight, we still have a very minuscule variation in the gravity. I mean, you can repeat the same calculation if we go towards the interior depth. So maximum depth, let's say 10 kilometers. We'll see that still gravity is negligible. While the density is constant for liquids, the density and pressure vary in a certain way for gases. If we assume that the gas is an ideal gas, then we know that P equal to rho RT. And this equation of state can be used to find out the pressure distribution in a gas. Say for an example, the atmosphere. So let us find out the distribution of pressure. So we have dP dz is equal to minus rho times G, and this rho is now a function of pressure, so it is equal to minus P upon RT times G. Therefore we can write dP upon P is equal to minus G upon RT times dZ. Let us integrate from point 1 to 2. Now we have already discussed that G is a constant. Moreover, R is also a constant. But what about T? Surely T is not a constant. We know that T actually reduces as we go towards higher altitudes. However, let us assume that it's an isothermal atmosphere. In this case, we can perform the integration rather easily. So we have on the left hand side ln P2 upon P1 is equal to minus G Z2 minus Z1 upon RT. Now we can choose Z1 to be 0 and P1 as the atmospheric pressure. Therefore ln P2 upon P atmospheric is equal to minus G Z2 upon RT. That is P equals PA e raised to minus GZ upon RT. So for an isothermal atmosphere, the pressure decays with altitude exponentially. So if this is the atmospheric pressure and this is the altitude, so this is Z equal to 0, the pressure will fall exponentially like this. However, in typical cases, the atmosphere is not isothermal. In fact, the temperature varies from 20 degrees Celsius at the surface to a temperature of minus 60 degrees Celsius at an altitude of 11 kilometers. That is the edge of the troposphere. So, if we employ the ideal gas equation in order to replace the density in terms of the pressure, we can write dP by P is minus G dZ by RT, where T is no longer a constant, but T is given by T0 minus beta Z, where beta is called as the lapse rate. So I urge you to find out the pressure variation for this non-isothermal atmosphere. We've all noticed how carbon dioxide suddenly starts bubbling from the liquid when we open a bottle of soft drink. The fact is, carbon dioxide gets dissolved into the liquid because it is a pressurized container. So, what happens when you pressurize gas? So consider this container, and this contains water, and this contains CO2 or N2 or whatever gas you have. If the pressure over here increases, then the partial pressure of each of these components also increases. Now Henry's law tells us that the solubility is some constant times the partial pressure. As a result of this, if we increase the partial pressure, the solubility increases. Similarly, if suddenly you reduce the partial pressure, the solubility decreases and the gas comes out from the solution. This is what you see when you open a soft drink bottle. So when a diver descends to a depth of 30 meters, the pressure is approximately atmospheric pressure plus rho gh. So this is equal to 10 to the power 5 plus rho is 10 to the power 3, g is approximately 10 and height is 30 meters. So this is approximately 4 times 10 to the power 5. So this is approximately 4 bar. So the solubility of nitrogen at 4 bar compared to the solubility of nitrogen at ambient conditions is proportional to the pressure of nitrogen at 4 bar and the pressure of nitrogen at ambient conditions. So this partial pressure obviously depends on the mole fraction and all these things, and it follows completely from physical chemistry. So essentially you have a higher solubility of N2 in blood, a lower dissolution of carbon monoxide from blood, and a higher absorption of of O2 also in blood. Now N2 and O2 can combine to give NO, which is nothing but laughing gas. So a higher concentration of N2 and O2 and the lower dissolution of CO give rise to an intoxicating effect. They give rise to a sort of tranquility for the diver. Divers have often said that they can hear fish talk and many other bizarre things. And when the diver actually starts coming up, the solubility again starts going back to its usual value. N2 and CO start coming out from the blood into the normal breathing conditions, and the diver can regain his consciousness and mental state. However, if the diver ascends too fast, then sudden release of nitrogen happens in the blood, and that causes bends in skins, and this is also called as decompression sickness. A helium oxygen mixture called as heliox is used in order to avoid nitrogen narcosis. The mixture is such that it reduces the difficulty in breathing at elevated pressures, and that it tries to maintain a mole fraction so that the partial pressure of oxygen is maintained. Moreover, it contains no nitrogen, which avoids the issue of formation of NO altogether. So that's it. This is the fluid mechanics of a diver. Why a diver should be aware of all these kinds of effects. Not knowing these can end up quite lethal. So I hope you enjoyed this particular lecture, and I'll see you next time with another video. Bye.